So this is a project, sorry, find the laser pointer here. Is it on there? No. Is it this? No.
A separate one.
Oh, thank you. Thanks. So this is a project that Mike Fall and I recently carried out on angular momentum and galaxy formation. For those who were here last year, this is a refinement of the talk that you heard. We've now have the paper in press with the AppJ supplement. So this is revisiting kind of a very classic way of looking at galaxy formation in terms of some fundamental physical parameters. Let's say characterize a galaxy as a spherical cowl with some 3 parameters describing the mass, energy, and angular momentum. For observers, those might be roughly related to luminosity and different combinations of some simple observables, the sizes and the rotation speed of galaxies. And the idea is that these are in principle, could be conserved quantities. And if you can understand the conservation or lack of conservation of these quantities, you might understand something about galaxy formation. So now this talk is primarily about the angular momentum. And one related parameter is the spin, which you probably all know and perhaps love. The spin parameter here defined as this combination of those quantities. It turns out in hierarchical structure formation to be, on average, very robustly known in a lambda, well, in a hierarchical galaxy formation to be predicted as this fairly weak spin parameter that's on average, a universal constant with redshift, with mass of the halo, going back, for example, and this is this paper by Barnes and Efstathiou. So this gives us some robust initial conditions on galaxy formation. Now we can't actually do things like understand the conservation of this as a physical parameter. But you can do that with mass and angular momentum. So this is taking the same plot, spin parameter, the halo, and mapping it into this space of specific angular momentum, J over m, versus mass of the halo. And it turns from a flat distribution into this characteristic increase here. So this is the plot that I'm going to be showing a lot in this paper, both from theory and from observations, using this kind of plot to understand galaxy formation. So now, using this to set our initial conditions for galaxies, you can convert this spin parameter here into the physical parameters. If you know the virial mass of the galaxy, on average, you have a robust prediction for the specific angular momentum. And in this plot here, I represent that as this mean line here of the initial conditions of the galaxies. So this is what we know from theory. This is not something that's changed in decades. So whatever galaxies we see today have to be linked back to this basic relation by some processes that evolve galaxies in this plane. So just to show that schematically, here we go with that starting initial conditions again, and we populate that with dark matter halos. And let's just look at the gas in those halos. Let's say we collapse the gas. And conserve, for our simplest assumption, let's say they conserve perfectly the specific angular momentum. So you've got some fraction of baryons that belong to the dark matter halo moves you over here in the diagram. And let's turn that gas into stars. And again, for simplicity, conserving perfectly specific angular momentum, and you move over here. So what you end up with, and then now let's say, okay, we're going to, for example, lose some specific angular momentum, and we go down here. Now what we've got is, this is something we can observe. We can measure these quantities, J and M, observationally, put them on this plot. We have our initial conditions here, and we've got a pretty simple characterization of linking the unseen dark matter to the visible galaxies with this combination of parameters, the angular momentum conservation parameter and the star formation efficiency parameter. So here are observations from 30 years ago that Mike put on this diagram, and you may have all seen this at one point. These are the spiral galaxies, and these are elliptical galaxies here. And you can see this tight correlation for the spirals in particular. And the way you get at this diagram, I'm not going to really discuss in the talk how to plot how these numbers are made, but you can think of it as a connection Okay, I just lost the battery. Between rotation velocity and size of the galaxy. Gives you specific angular momentum. And it turns out that this observed relation for spirals matches pretty nicely what we expect from this very spherical approximation for galaxy formation with a small amount of scatter and roughly order of 1 conservation of specific angular momentum. The elliptical galaxies look similar, but as though they've lost more specific angular momentum. Well, these are data from 30 years ago, and the question is how much of that has changed in intervening years. This plot has been used as a constraint in galaxy formation simulations, which a lot of you have worked on personally. And this is showing the plot again with Mike's data from '83. And these points here are some early simulated galaxies in what was called the angular momentum catastrophe. You see there's been a specific angular momentum loss by 1 or 2 orders of magnitude, which is clearly unrealistic and continues to be a struggle for a lot of simulations to reproduce the observations and become a benchmark. Here is something much more recent. And the point here is not so much to compare, again showing the same data, not so much to compare to the data, but just to showing with 2 different methods, the ARIPO and Gadget, and you get a spread of, say, a factor of 2 in the specific angular momentum, showing that the simulations have not yet converged on this to within a factor of 2. So it continues to be a benchmark, and we continue to hope for convergence from the simulations to agree with the data. So there's been a lot of work looking at spiral galaxies as a benchmark, the specific angular momentum mass correlation as the benchmark for spiral galaxies. What's been a bit forgotten are the elliptical galaxies, which were also on the original plot. And so what we wanted to investigate was, well, are the elliptical galaxy data from 30 years ago correct? What about S0 and SA galaxies, which were not there in the original diagram? Do they fill in the gap you see between spirals and disks? And now if we try to compare these again to the lambda CDM model, how do these match up in kind of a simple approximation? And another question is, well, if ellipticals turn out to be low there, do we expect them to be low for some reason, to have lost more specific angular momentum? And there was some thinking about this over the years, that in fact we expect the specific angular momentum of ellipticals to be higher than spirals rather than lower. And the idea being that if ellipticals are formed in major mergers, then that orbital angular momentum that comes in the merger causes the merger remnant to have a higher angular momentum than average, or specific angular momentum than average. And you can see here some plots of specific angular momentum versus time expansion parameter, and there's these jumps up every time there's a major merger that's occurred. So that seems to be contrary to the plot from Mike's paper from '83, where the ellipticals were lower in the diagram. Well, there's a handy explanation for that, which is that, well, maybe we're just not measuring observationally all the angular momentum in the ellipticals. And if you look down this lower plot here, there's this with the lambda's internal spin with binding energy, and this is in a major merger remnant. The idea is that a lot of the angular momentum's gone into the outer parts where you can't really observe it, and that's why they look like that in the JM diagram. So is that correct? Well, as Gene mentioned yesterday, you really need to go to the outer parts of elliptical galaxies to get at their total angular momentum, beyond the regions covered by, for example, by Sauron, say to 4 or 5 effective radii to measure the totals, to have a good, be confident that you're measuring the total angular momentum. And there were some pioneering attempts to look at the outer rotation of elliptical galaxies. M87 is a famous central cluster galaxy, and this is Sin A, and GC 5128 thought to be a merger remnant. And these early observations saw a lot of rotation in the outer parts, seemed to support this idea that, oh, well, that's where the angular momentum disappeared to. It went to the outer parts. Well, it turns out that those papers were pioneering, but a little too pioneering, that they got the wrong answer. With more modern, much more accurate data, it turns out that these outer rotation spikes are not there. So, that's right, but not nearly as much as was thought. So that's the question. We need to actually calculate the angular momentum and see what it looks like on the diagram. The angular momentum still does increase with radius. And this is a sort of a summary plot of some modern data on ordinary elliptical and S0 galaxies with effective radius getting out to, say, roughly 5 effective radii, where we can start to really constrain the specific angular momentum. What you can see is they typically don't look like they're rising. In fact, if anything, they tend to be declining. The rotation is declining with radius. So there isn't some vast reservoir of hidden angular momentum in their outer regions. So now, skipping over the details of how we do it, but this is putting the actual data on the plot from the various galaxies from the literature, 100 galaxies from the latest type spiral, earliest type elliptical. First time this has ever been done for the full range of Hubble types. Stellar specific angular momentum versus mass. And you might be able to kind of see the point color coding here, but this top line is the spiral relation and for the latest type spirals, and this is the ellipticals down here. So it's basically what Mike found. With slight difference in the offset, but the ellipticals persist in being a lower specific angular momentum, and with a roughly parallel relation. And the S0s do turn out to be intermediate between the spirals and ellipticals, as you might have guessed. So this now becomes, this kind of, some of these galaxies have, sizable error bars, but basically these correlations should not go away. This is fundamental observations of galaxies, which should be constraints on any theory of galaxy formation for all time. Now, looking at this in a little more detail, we tried to break galaxies down into their bulges and disks. And here, these are just the disks. These top blue points and the red points are ellipticals. Now, we tried to look at the bulges of spirals. This is much more difficult than the overall galaxies. So those are these gray stars. And down here, we don't really believe the data too well, what we've done with the data. But up here, they seem to overlap pretty well with ellipticals. So it's as though bulges, even though lots of other scaling relations don't match ellipticals, when you look at angular momentum versus mass, they do match up. So suggesting, and these are mostly classical bulges up at the high masses, suggesting the classical bulges and ellipticals are part of the same family or formed in the same process. And on the right-hand side is a residual of specific angular momentum versus bulge fraction. And you just see that there's a model curve there plotted against the data, and it seems to all hang together fairly nicely as far as we can tell. The intermediate types have intermediate specific angular momentum because of their bulge fraction. And it brings us to a way of describing galaxies, and this is not really new, that describing galaxies as a bulge and a disk, but what is new is that we're putting this on a more physical basis of characterizing these by their specific angular momentum. That the reason you have a disk is that it has a high specific angular momentum, and a bulge is something with a low specific angular momentum. And then the whole Hubble sequence would be replaced, instead of as morphology and spiral arm types and things like that, the Hubble sequence is really a bulge to disk sequence with these specific angular momentum relation. So now getting on to theory, now connecting to this lambda CDM schematic that I showed at the very beginning, again, the simple spherical model. Now if you put in there, up there is a scaling relation you predict with your lambda, your spin parameter, which is something you can predict pretty robustly on average, and then just these two simple parameters, fj and f star, the star formation efficiency and conservation parameter of specific angular momentum. Well, if we subtract sort of the mean relation, we get these residuals, and you can see here this is a histogram of residuals, and the main thing to look at here is this is all reweighted by frequency of galaxies. This is versus what you expect the Gaussian distribution or log normal distribution of halo spins predicts this for the halos, and the spiral galaxies roughly match that. So overall, the theory predicts things fairly well. Now what happens is that the tails are not quite right. There's missing these high ones here, and then there's this extra tail of low spin here that are the elliptical galaxies. So there's a couple ways, very simple, extreme ways we could try to model the galaxies. If you start with these dark matter halos and say, okay, let's populate the low spin halos with ellipticals and the high spin halos with spiral galaxies, and maybe that's what's going on. Why do these have these different specific angular momenta? So here's the real data in the center. This is what we're trying to get with these models, and on the right is doing the spin bias, and it turns out it doesn't work basically because at high masses. You've got lots of ellipticals, and they can't just be the extreme low spin tail of dark matter halos. So we could take another extreme case and say, okay, well, let's just say they all have the same types of halos, but they lost different amounts of specific angular momentum with a different FJ factor. We call that variable FJ parameter. And that on the right seems to work pretty well. So that works. That doesn't work. This does. And of course, the truth could be somewhere in between. So just to summarize, in terms of a way to quantify galaxy formation, this is the star formation efficiency versus angular momentum conservation efficiency. And these are observations, not quite direct, but indirect observations for spirals are up there. The high star formation efficiency, high angular momentum conservation efficiency, and both parameters are low for the ellipticals. So we need some mechanism for doing that. And the idea is that there's been a lot of work on getting this to work out for spirals and simulations and analytic models of some kind of feedback, for example, to remove low specific angular momentum gas, and trying to get ways to get this to work for spirals. Well, whatever you get to work for spirals, you need to, in the same self-consistent model, need to not to work for ellipticals. You need to lose the specific angular momentum for ellipticals. So we need to get them both right at the same time to reproduce reality. And again, I'm not going to get into the purpose of this study we did is not to really figure out how galaxies are assembled, but to give a target or a benchmark. And so there's lots of simulations out there in full, going much far beyond our simple spherical cow model. And the idea is whatever is happening there, we need to understand why at some level it reduces to this simple spherical model that reproduces the observations with basically zero additional scatter as far as we can tell. And we've kind of done some very hand-wavy ideas of how some processes might work to give you the galaxies you observe. And the idea is that this is the J over M diagram, because there are physical parameters that are conserved. I mean, if you lose J, it's got to go somewhere, and by some real physical process. And you can create vectors in this diagram. Real physical processes have specific vectors here. And you can't just move things around. You've got your initial conditions of this lower gray line from the dark matter halos, and you need to get to the observations with a real process. And you can't just make up some vector to do that. And for example, outflows and stripping move you in these different directions here. Mergers are on the right, depending if they're major mergers or minor mergers. We kind of had some hand-wavy ideas on how that might work. Or a collapse bias that say the elliptical galaxies collapsed earlier relative to the spirals and stopped forming stars. And it turns out to be somewhat hard to get these things to work out to reproduce the observations. And this is something that can be looked at in more detail. So just in summary, again, this is the specific angular momentum versus mass, this in stellar mass and specific angular momentum. The first compilation for all galaxy types, becoming a benchmark for galaxy formation theory, using modern extended kinematics data for early type galaxies that we can finally be confident we're getting the right answer. And we continue to see this offset between spirals and ellipticals, which is parallel and with a fairly tight scatter in each galaxy type, which is equivalent to the scatter you expect in lambda CDM halo spin, the scatter of the spins. And it appears you could model this with a difference in angular momentum conservation, where the spiral galaxies have conserved most of theirs, elliptical galaxies have lost 90% of theirs. And I'll leave that as a challenge for theory. Thanks.